Hi girls. We're going to start with question 3. Question 3 says, calculate the orbital period of a satellite. Answer an example problem 2 and check your progress 8 from page 172. Now, in this objective, we talked about satellites and how Newton's thought experiment was the beginning of launching satellites in space. We learned that satellites move in a uniform circular motion with the same speed, the constant speed around Earth. To find the speed of a satellite, we use this equation right here. V equals to GME over R, where G, remember, is 6.67 times 10 to the power of negative 11. ME is the mass of Earth in kilograms, Earth in kilograms. Sometimes the satellites would be orbiting planets other than Earth, like Jupiter or Mars or whatever it is. You substitute the mass of that planet. Sometimes it is the sun, and we have a planet orbiting around it. Then you substitute the mass of the sun here. All right. R is the orbital radius. It is the distance between the satellite center and the center of Earth. And you can see that this resembles the radius of the satellite's circular orbit. So R is the orbital radius, or you can say the distance between the center or the satellite. Oh, satellite is just one T. And the center of Earth. Now, the surface of Earth, it makes a huge difference. And it's measured in meters. Now, sometimes in questions, they don't give you the orbital radius straightforward. Rather, they give you the height of the satellite above the ground, which is this distance right here. This is called the height of the satellite above the ground. And they also give you the radius of Earth. They give you the radius of Earth. And this is RE, the radius of Earth. If he gave me the height of the satellite above the surface of Earth and the radius of Earth, then you can find the orbital radius by adding them together. If you add the height of the satellite above the surface of Earth and the radius of Earth, you will get the orbital radius R. So R equals to H plus RE, where H is the height of the satellite above the surface of Earth, and RE is the radius of planet Earth. That's in some of the questions. But if the question gave you the orbital radius of a satellite straightforward, then this is an easy question. You just substitute it in the equation. All right. The period of a satellite. Now the speed, of course, will be measured in meters per second. The period of a satellite is how much time the satellite takes to make one complete revolution around the planet. We can find it by multiplying 2 times pi times the square root of r cubed over GME. These are the same symbols here, they're just in a different rearrangement. So T equals to 2 pi the square root of r cubed over GME, and V equals the square root of GME over R. Now, from these two equations, you can conclude the following, that the speed of the satellite is inversely proportional to the orbital radius. This one is up in the numerator, while this one is down in the denominator. So, because they are in different spots in the equation, the relationship between them is inverse. That means if the orbital radius increases, the speed of the satellite decreases. And vice versa, if the orbital radius decreases, that means that the satellite is closer to Earth. Then the speed of the satellite will increase. So this is the first thing we conclude. The second thing is the relationship between the period and the orbital radius. You can see that the orbital radius in the period equation is in the numerator, just like the period. So because of both of them are in the numerator, the relationship between them is direct. It's a directly proportional relationship. That means if the orbital radius increases, that means that the satellite became further and further, then obviously it will take more time to rotate around Earth. And the opposite is correct. If the orbital radius decreases, that means that the satellite becomes, closer to Earth. Then it will take less time to make one complete cycle around Earth. So again, the relationship between V and the height of the satellite is inverse, but the period of a satellite and its height is direct. You can also conclude that the speed of the satellite and its period, they don't depend on the mass of the satellite. They are independent of the mass of the satellite. So whether the satellite is small or big, V and T, the speed of the satellite, and its orbital period, don't depend on its mass. They only depend on the height of the satellite, or in other words, its orbital radius. And this example says we have assumed that a satellite orbits Earth 225 kilometers above its surface. So in this case, he gave me the height of the satellite above the surface of Earth. He gave me H ارتفاع الساتلايت عن سطح الأرض يساوي 225 كيلومتر. So he gave me H. Given that the mass of Earth, so here he gave me ME, the mass of Earth. And the radius of Earth, so he gave me RE, the radius of Earth, the radius of Earth. نصف قطر الأرض. What is this? What is the satellite's orbital speed and period? So he wants me to find V and T, the speed of the satellite and its period, how much time it takes to make one complete cycle around Earth. Now the first thing, so how much is V and how much is T? The first thing I need to do is to make sure that all of the units are base units. You can see here that the height of the satellite above the surface is in kilometers. So what should I do? I need to convert it into meters. Remember the scale. If I want to convert from kilo unit to the unit, I need to multiply by 1000. So in order to convert 225 kilometers into meters, I need to multiply by 1000. That will give you 225,000 meters. So this is the height of the satellite above the surface in meters. After that, I need to find the orbital radius. So as you can see here, he didn't give me R, the orbital radius. He gave me H, and he gave me RE. So to find the orbital radius from the center of Earth to the satellite, I need to add the height of the satellite plus the radius of Earth. So 225,000 plus the radius of Earth given in the question to be 6.38, 10 to the power of 8 meters. There's no need for conversion here. Using the calculator, 225,000 plus 6.38 times 10 to the power of 8 gives you this really long number. Is it power of 8 or 6? See, it is 6, not 8, sorry. Use the calculator again, correct the mistake. Instead of 8, we put 6. We get 660,5,000. 660,5,000 meters. So this is the orbital radius, which is the distance between the satellite and the center of Earth. Now that we have R, we can use the two equations to find V and T. G M E over R, the square root of 6.67 10 to the power of negative 11. Always write what you need to put in the calculator. Don't go straight forward to the calculator, even if it takes you time. Using the calculator. Oh, give you 7,764.5. So this is the speed of the satellite. To find the orbital period, we're going to multiply 2 times pi, which is 3.14, times the square root of r cubed over GME. 2 times 3.14, the square root of r cubed, which is 660,5,000 cubed over 6.67 10 to the power of negative 11, 5.97 10 to the power of 24. Use the calculator. Oh, I forgot times 2 times pi. Let's repeat that again. 2 times pi times square root of 660,5,000 cubed there you go, 5344.9. 5344.9 seconds. This is the question mentioned. Here it says Neptune orbits the Sun at an average distance given in the question. So this is the orbital radius given in the question, which is the distance between the center of the Sun and the planet, which allow gases such as methane to condense and form an atmosphere. If the mass of the Sun, so here he gave me the mass of the object that the planet is rotating around. Calculate the period of Neptune. Calculate the period of Neptune. So he wants me to find the period. So 2 pi, the square root of r cubed over gm. Now, instead of me, this planet is rotating around the Sun. So I'm going to put ms, the mass of the Sun. It's the mass of the thing that we are rotating around. 2 times pi, the square root. Now r here is given جاهزة 4.496 10 قوة 12 نحطها بين قوسين نعمل تكعيب على الآلة الحاسبة على 6.67 times 10 to the power of negative 11. MS, the mass of the sun, 1.99 times 10 to the power of 30. Use a calculator. Now be careful with the calculator. See, anything makes a mistake. 2 pi times the square root of fraction cos 4.496 times 10. See the times down? To the power of 12, and then close bracket, cubed over 6.67 times 10 to the power of negative 11 times 1.99 times 10 to the power of 30, then equal. Oh, that's the orbital period of planet Neptune. 5199 12037. Of course, this is in seconds. If you want to turn it, for example, into minutes. So 1 second has 60 minutes, and 1 minute has, or 1 hour has 60 minutes. If you want to convert like from hours to days, that's 24. From days to years, that's 365 days. But if you want to convert that number from seconds into years, so divide by 60 times 24 hours times 365 days, that's going to give you a 164 years, point something, 0.8. Here are some other questions that you can look at.